this was at the old time how we expect this the so-called Parton soup for the proton. So you have the 2u. How you view this 2u? If you're making the integration of this momentum distribution, the total area is the number of the density. So they'll give you 2u and 1d. And over there you have some C-quark. The C-quark, specifically we use the antiquark to label it. So we have a U bar, D bar, and S bar. And if you assume the so-called SU3 symmetry, that means the quark mass for U and the D and S are the same. Then this C-quark, how this gluon splitting into UU bar, DD bar, SS bar, the probability should be more or less similar or the same. So that is why this distribution should be identical over there. But then here is kind of a naive expectation. You still need to get in the proof from the experiment. So there is this kind of a Gottfried field sum rule. That means if you measure this structure function of using the proton, subtract the structure function of neutron. I didn't show it, but if you trust me, this difference, if you measure the structure function here by changing your topic, getting these things, and you subtract it, then you can divide it into the contribution from the valence quark term and the C quark term. Suppose this U bar and the D bar are identical. Then this term, we know due to the valence quark, this gives the contribution 1, and this should be out. That is 1/3. So this Gottfried field sum rule provides an experimental way to check whether this kind of expectation U bar, D bar are really true. Okay, so there is a lot of the experimental work by these various measurements. They measure the difference of this structure function by changing their targets like a proton, neutron, across certain region of the X. And they're making the integration of this value. Okay, so here is the expectation 1/3. So with this various measurement, they really confirm this Gottfried field sum is actually deviated from the 1/3. So that means this kind of a naive picture is actually wrong. Okay? Then what would be the explanation? Okay? Some people still believe that maybe this kind of because experimentally you can only making your measurement is only on a limited range of the X. So there is still some leftover here. So it's rely on some kind of extrapolation. You have to get it down here, making the whole integration. So there is so-called systematic error over there. So maybe this kind of a systematic error can account for this deviation over there. Okay, and then there is some kind of the so-called charge symmetry breaking effect. Okay, that don't involve it. And of course, the other more naive picture is maybe U bar and the D bar. The distribution is really different. However, the one drawback of this Gottfried field sum, because it only can tell you the integration of this difference. But in reality, it has no constraint. For example, this is D bar and a U bar difference as a function of X. All of this red curve and the blue curve give you the same integral value. But using this DIS, the structure function method, you have no way to distinguish whether the blue one is true or the red one is true. So that comes out that you have to rely on the other different approach to confirm it. That is another process. So previously I introduced you to find out the quark structure is to use the lepton, high energy lepton, to scatter the structure, to find out the structure. Another process which is also highly commonly used in the high energy physics is the so-called Drell-Yan process. So that was taking the two authors. One is Drell. I guess he's a well-known guy, which he wrote a famous textbook for particle physics. And another is actually the Yan Dongma. So he is actually a graduate from NTU. Okay. So their propose is actually this process is during the collision of two hadron. You can view as one process is the contribution. The process is the quark and the antiquark annihilate into virtual photon, or even if the energy is high, it can even go to the Z meson, and then they can electromagnetic decay into a dilepton. So one of the good things for this Drell-Yan is because this lepton can only interact with the environment through the electromagnetic interaction instead of the strong interaction. So that's making the experimental detection rather clean. Okay, but through this Drell-Yan, you find out you have another way to determine the quark or antiquark content inside a hadron. Okay, so experimentally, if you were be able to detecting this Drell-Yan process by study the ratio between using proton hits deuterium and also proton hitting proton, and if you making some using the detector acceptance to select out of some certain range, you can more or less approximating this ratio of the cross section. It will be directly reflected the ratio of the D bar and the U bar. If you okay, I didn't go through this derived, but that is the case. Okay, so this proposal was first verified by an NA41 experiment at the CERN, as the Europe CERN, in 1994. So they only providing 1 point here, but indeed they observed this. Previously, we want to make in a gas, but only we can only get the integral value. Okay, so right now we really pin down at the certain X region. This D bar and the U bar ratio are not 1. They are actually 2 over there. And then there is another following experiment carried out in the Fermilab, which is provide a detailed mapping of this flavor structure of the D bar, U bar across a wide range. So it's starting from the very almost symmetric distribution at the very small x here, then gradually the asymmetry build up, and then it's kind of the getting down here. And of course, when it go to a slightly large x region here, the error bar getting worse. Okay, so through these things, so here is right now our more or less our we have some kind of with the contribution with many DIS and the Drell-Yan experiment. This is providing this is the so-called Parton density distribution, which is how these various content, as I introduced you, like this 2U and the 1D. But here, there's a different line, this U bar, D bar, and S bar. You see this green and the blue obviously has the different distribution by determining this. So this has already been determined by the experiment. And specifically here show you with the contribution with the Drell-Yan experiment, which is actually constrained. If you only use the DIS, which have no specific sensitivity for quark and antiquark, the error range is wide. But with the additional more constraint with the Drell-Yan, which can actually give a better constraint for the D bar and the U bar asymmetry. Okay. So so I just tell you is the U bar and the D bar. How about the S bar, strange quark? So strange quark, the way for looking into it, which is normally it's rely on a more sophisticated approach. You have to use the neutrino scattering. Neutrino can by exchange the W boson, interact with the S or D, convert it into the C quark, and then this C quark can decay into the open chum. This open chum decay contain another muon. So experimentally, you detecting also dimuon event in the using the neutrino scattering. Okay, so the story known over there is roughly this: the overall S and S bar content is about 1/2. So because of the S quark, the mass is heavier. So the S and S bar content is only 1/2 of the U bar and the D bar. And over there, up to now, the asymmetry, as I told you, U bar and the D bar, there is asymmetry. But people were asked whether the S and S bar up to now, there is no, experimentally, there is no very firm facility. So this is the so-called NTU-CTP experiment. This is up to now the most precise measurement for the S minus S bar, the asymmetry between the strange quark. Over there, unfortunately, the error bar is actually too big. So there is still no conclusive information on these things. Okay. Okay, maybe I will skip this one. Okay. So right now there is operating of this LHC. So LHC through the production of the W boson or the Z boson. So W is composed of the quark and the antiquark, and the Z is similar like a virtual photon, which is also like a QQ bar over there, which is actually can also give you a constraint on the C quark in terms of C quark. Okay, so I forgot. So okay, it's a while ago, 4 or 5 years ago. So ESSER has a very interesting result from this W and Z. Somehow they find out the ratio, the strange quark ratio with the D quark ratio is very large, is 1, which is a little bit surprising because on the neutrino experiment tell us this fraction is only 1/2 instead of 1. But I think I didn't put in. Later on, the CMS, I think, has a measurement, also similar measurement, but that was more consistent with the 1/2. Okay? Okay, so here I just introduced experimentally we do observe the U bar has a different X distribution as the D bar. Then you might want to ask is why? Why? What should be the cause for these things? Okay, so quantitatively it can be explained by the Pauli blocking, because even I tell you the gluon fluctuates into UU bar has a similar probability as the gluon go to the DD bar, but because originally inside the proton there is already 2U and 1D. So this 2U valence quark actually introduce more Pauli blocking effect to the gluon go to UU bar, then gluon go to the DE bar. So that more or less suppress this kind of the effect in gluon go to the UU bar. So this gives you some kind of a qualitative understanding why this D bar is has a more. Okay, because previously I showed you these things. D bar is actually has a more content than the U bar. Okay, so this provides a qualitative understanding, but quantitatively, it's has difficult to match the experimental measured number. So there's various model of it. So right now, I think in the community, the most accepted physics picture is to go through the meson cloud model. So if you imagine the proton, so proton can be also viewed as it's surrounding by some pion meson. So it can also fluctuate into like a neutron plus a pi plus, or proton pi 0, and but there is no other pi minus, because they were making this proton to be, of course, over there, you might consider something like the delta delta, but delta is not but if you limit it to the ground state nucleon, this is only possibility. So then if you count the content of this pion cloud, it will automatically give you a more D bar through this surrounding this outside things. Okay, so pion cloud is actually right now can provide a more quantitative way. Sorry, I will skip this one because of the time. So right now, all this basically invoke of the meson cloud can give the best quantitative description why this you observe more D bar than U bar. So experimentally, there is one interesting point on the large X, which is showing instead of the D bar is greater than U bar, is maybe on the very large X side. Is there any possibility U bar can be greater than D bar? So that's the turnover of the whole story. So that's this interesting point actually bring up to a next experimental effort, which is again in Fermilab. We proposed the experiment and carry out over there. Instead of using the 800 GeV tevatron beam, we use the main injector beam. So with the lower energy, but they can be pushed us to the large X side over there. Okay, so this was an experiment, which is my group and NTU, sorry, not NTU, NKNU, 高师大. They are getting involved, and there's main collaborator from United States, and there's Japan get involved. Okay, so we're starting this project. It's actually quite a while ago, almost 10 years ago. So it takes a while to prepare it. So even we get in 2007, but the commissioning run started not a very long time ago, 2012, and then we go through 3 of the physics round, and the final physics round will be started in this month and will be end in the next August. So up to now, this is probably the whole beam time we can already we can get from the Fermilab. That will probably conclude all the data taking. Okay, so this is the experimental way. Of course, it's not as fancy or beautiful as you will see from the LHC experiment, because this is the fixed target. So basically, the proton beam will be extracted from the main injector and delivered to our beam area, and it hits the target here. But because of the radiation background is very high, so it has to be shielded by a lot of this concrete and the lab rat. So you will not be able to see the target region here. And then we detecting the decay, the outcoming the lepton, which is the muon pair, by various this spectrometer. Okay, and hodoscope work as a trigger device. Okay, so we more or less prepare all of this readout by academic Sinica group. Okay. I apologize for some of you already seen these things. Okay, so this is the preliminary result from 2015. Okay, so as I tell you, if you do the targets, if you get in the cross-section ratio as proton hits deuterium times divided by 2 times the pp, it's more or less give you the idea how these things over there, how this d bar and the u bar ratio. So previously this A66, they measured this cross section, okay, and this blue point is from our sequest. So systematic is labeled, characterized by this green band here. Okay, so you can see it's a little bit surprising. Previously, of course, suppose we can, from here, maybe you see, oh, how come we have some deviation from ACT6, right? ACT6 measure here, we measure here. How come on the overlapping X region here, how come you have the deviation? But there is things you have to take care is we are measured our main acceptance for the Drell-Yan pair are at a different Q square. The invariant mass are different region. So if you furthermore changing these things to be this one and taking into account the QCD evolution effect at the different region, then this is the final extracted result. Actually, you find out you actually have a good agreement with the ACT6, which is showing this D bar U bar ratio here. But then, right now, our measurement indeed showing the deviation.
So the ACT6 data including systematics?
Not showing here, but they are actually not that large. Maybe, yeah, if I remember, they are more or less like this, maybe point, in terms of this, maybe at most 0.1, 0.1, 0.2.
But not in the error bar.
Not including the error bar here.
So
Yeah, so I know it's
Sorry, Wen-Chen, can you go back to the previous page? So you have a calculation and also your own data, right? How come they do not agree with each other?
You mean our data and our calculation, right?
Yeah.
Yes, because the calculation was based on the parameterization of ACT6. So because all of this CT10.
Then how come you don't agree with the black line?
The black one, this black one is for ACT6, right? And this red one is I use the current CT10 to calculate A906 result.
So they have different Q square.
Okay.
Yeah. No, but Zhengwei's point is maybe from here you still see the deviation.
Right.
But this PDF input is based on the CT10, which was constrained by the ACT6. So that is why this has to be go down, because their PDF was using the ACTs as an input.
Another question is, why are your data? Why do your data have worse resolution compared to E866?
Worse? You mean where is worse?
Well, you have a bigger error bar, uncertainties, right?
No, for example, here we are better. We are definitely better.
Vertically, yeah. Horizontally, most of the.
Oh, that was due to the binning, because here we want to put the same meaning in principle you can reorganize. Of course, you can reorganize your data beam, but definitely previously ACC6 due to the beam energy they can only limit it up to here, but right now we starting to get in the sensitivity down to
Can
here.
you go further down in X?
You mean here?
Yeah.
No, we stop here. So everything gets shipped.
So the target is the same, similar or not? Because the it's a liquid target that can be totally different, and you have a very different.
Okay. Wow. This is a very good question. So right now, I think the biggest systematic we have to pin down right now is actually how pure our deuterium target is. Deuterium target is very tricky. It always gets some contamination over there. Yeah. That's something.
Well, I still wonder, it's the same kind of liquid target or not between A66 and Sequest. It's redesigned.
No, I think the target cell is basically the same.
Target is the same.
But
Of course, the feeling is different. I know.
Yeah, the feeling is
Biogenic
different.
is very different.
Okay. Any more questions?
Actually, I still remember because we used that, maybe the same one, we used that liquid target before. And
I think so, maybe.
and there one time actually, I forgot it's deuterium or hydrogen was boiling. So the lava actually going through the beam.
Really?
Yes.
Okay.
I had that kind of incident before.
Yeah, okay. So right now, of course, we are a little bit, we have a strong debate is whether we want, even though we don't think that with 1 more years, because this is almost 50% of our total statistic expected. So with another factor of 2, probably these things cannot be changed too dramatically, unless we are making some mistake. Okay, but obviously this is the big difference here. Of course, yeah, here is maybe okay,
if you
but
don't calculate the so-called significance, what's the significance right now above, say, 0.224?
mhm. You mean we should calculate it?
I think you should
Okay.
calculate.
Mhm. Okay, that's a good suggestion.
You can
and then-
see it's inconsistent. I don't know, but I don't know the significance.
Mhm. Okay. Okay. So anyway, so this is some kind of a more new result on this U bar and the D bar. So that is how you see experimental life. So maybe if you have some measurement, we're showing the consistency with the previous experiment. Even some of the collaborators, they are overlapped. So how do they deal with these things? That's a little bit tough. Okay, so final point I want to make is for the LHC actually through the W and the Z measurement. For example, here is some plot showing on the LHC 14 TeV. So you see, because it's go to very small X region here. So this kind of previously the U bar D contribution is completely dominated. But right now, when you go to the higher energy, in the mid rapidity is really shifted to a very small X region. So this, you starting getting a actually relatively good sensitivity about even the C bar, the Chang and the strange sensitivity over there. Okay, and even more surprising like Z0, okay, strange quark can do. So by measuring the W and the Z production in the LHC, actually provide a very good constraint on this C quark. But of course, they are on the very small X region here. So in the future, in the United States, there is a proposal for the EIC, which is the electron-ion collider. Over there, you will be able also cover quite a large of the X and the Q region here. Okay.